Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
John von Neumann's Mathematical Foundations of Quantum Mechanics, published in 1932 but based on lectures and papers dating back to 1929, represents a watershed moment in the formalization and rigorous presentation of quantum theory. Prior to von Neumann's work, quantum mechanics, although demonstrably successful in explaining a range of atomic and subatomic phenomena, possessed a certain mathematical ambiguity and lacked a universally accepted axiomatic structure. This ambiguity stemmed partly from the rapid development of the theory by physicists, who prioritized experimental validation and physical intuition over strict mathematical consistency. Von Neumann sought to rectify this situation by providing a comprehensive and mathematically coherent framework for quantum mechanics, grounded in the theory of Hilbert spaces and operator theory. Several factors converged to necessitate and enable von Neumann's groundbreaking contribution. The initial formulations of quantum mechanics, spearheaded by Heisenberg's matrix mechanics and Schrödinger's wave mechanics, appeared superficially distinct. Schrödinger demonstrated their mathematical equivalence, yet a deeper, unifying mathematical structure remained elusive. Furthermore, questions concerning the interpretation of quantum states, the nature of measurement, and the consistency of probabilistic predictions with deterministic evolution generated considerable debate. The Copenhagen interpretation, championed by Bohr and Heisenberg, offered a pragmatic, albeit somewhat philosophically unsatisfying, resolution to these issues. Von Neumann, however, aimed for a more rigorous and axiomatic treatment that would render the interpretation less ambiguous and more amenable to mathematical analysis. Another crucial element was the rapid development of functional analysis and operator theory during the early 20th century. Mathematicians such as Hilbert, Banach, and Riese had laid the groundwork for abstract vector spaces and linear operators acting on them. Von Neumann himself made substantial contributions to these fields, particularly in the development of the theory of unbounded operators. This mathematical toolkit proved ideally suited for formulating quantum mechanics in a precise and general. At its core, Mathematical Foundations of Quantum Mechanics provides an axiomatic formulation of quantum mechanics based on Hilbert spaces. Von Neumann postulates that the states of a quantum system are represented by vectors in a complex, separable Hilbert space. Physical observables, such as position, momentum, and energy, are represented by self-adjoint operators acting on this Hilbert space. The possible values at an observable can take are given by the spectrum of the corresponding operator. Furthermore, the probability of obtaining a particular measurement outcome is determined by the projection of the state vector onto the eigenspace associated with that outcome. A central aspect of von Neumann's formulation is his treatment of measurement. He distinguishes between two types of quantum evolution. The first is the deterministic evolution of a closed system, governed by the Schrödinger equation, which describes the unitary transformation of the state vector over time. The second is the probabilistic and irreversible process of measurement, which causes an abrupt change in the state of the system, known as the collapse of the wave function. Von Neumann attempts to describe the measurement process within the framework of quantum mechanics by introducing the concept of a measurement interaction. He models the measurement apparatus as a quantum system that interacts with a system being measured. The interaction is designed such that the state of the measurement apparatus becomes correlated with the value of the observable being measured. After the interaction, the combined system is in an entangled state. The measurement outcome is then determined by the state of the measurement apparatus. However, von Neumann's attempt to describe measurement solely within the quantum framework faced significant challenges. The measurement problem arises from the fact that the Schrödinger equation, which governs the evolution of the combined system, predicts that the system remains in a superposition of states rather than collapsing into a definite outcome. Von Neumann's solution involves postulating a separate projection postulate, which asserts that the wave function collapses upon measurement. This postulate, however, appears ad hoc and raises questions about the precise moment and mechanism of collapse. Von Neumann's work also includes a careful analysis of the uncertainty principle. He demonstrates that the uncertainty principle, which states that certain pairs of observables, such as position and momentum, cannot be simultaneously known with arbitrary precision, is a fundamental consequence of the non-commutativity of the corresponding operators. Specifically, the product of the standard deviations of two observables is bounded below by a quantity proportional to the expectation value of their commutator. This provides a rigorous mathematical formulation of Heisenberg's original heuristic argument. Another significant contribution of mathematical foundations of quantum mechanics lies in its analysis of hidden variable theories. These theories propose that the probabilistic nature of quantum mechanics arises from our incomplete knowledge of underlying deterministic variables. Von Neumann presented a theorem that appeared to rule out a broad class of hidden variable theories. His theorem essentially stated that it is not possible to reproduce all the predictions of quantum mechanics with a hidden variable theory that satisfies certain seemingly reasonable assumptions, including the assumption that the measurement of an observable yields the same result regardless of which other commuting observables are measured simultaneously. This theorem had a profound impact on the development of quantum mechanics. It was widely interpreted as providing strong evidence against hidden variable theories and as supporting the orthodox Copenhagen interpretation. However, in the 1960s, John Bell demonstrated that von Neumann's theorem relied on an assumption that is too restrictive. Bell showed that it is possible to construct hidden variable theories that reproduce the predictions of quantum mechanics, but only at the cost of violating von Neumann's assumption of non-contextual measurement outcomes. Bell's work reignited interest in hidden variable theories and led to the development of alternative interpretations of quantum mechanics, such as Bohmian mechanics. The immediate impact of mathematical foundations of quantum mechanics was substantial. It provided a rigorous mathematical foundation for quantum mechanics, which helped to solidify its status as a legitimate scientific theory. It also stimulated further research in the mathematical aspects of quantum mechanics, leading to the development of new mathematical tools and techniques. Furthermore, von Neumann's work influenced subsequent generations of physicists and mathematicians who built upon his framework to address more complex problems in quantum. However, von Neumann's work also faced criticism. As mentioned earlier, his treatment of measurement was considered by some to be unsatisfactory. The projection postulate appeared arbitrary and raised questions about the physical mechanism of wave function collapse. Furthermore, von Neumann's theorem on hidden variable theories was later shown to be based on a restrictive assumption. Despite these criticisms, Mathematical Foundations of Quantum Mechanics remains a highly influential and important work. It provides a clear and rigorous presentation of the mathematical structure of quantum mechanics, which has served as a foundation for subsequent research. Von Neumann's contributions to the mathematical formalism of quantum mechanics are undeniable. The legacy of Mathematical Foundations of Quantum Mechanics extends far beyond its immediate impact. Von Neumann's work has had a profound influence on the development of quantum information theory, quantum computation, and quantum cryptography. These fields rely heavily on the mathematical tools and concepts developed by von Neumann, such as Hilbert spaces, operators, and entanglement. For instance, the concept of a quantum bit, or qubit, which is the basic unit of quantum information, is based on the notion of a quantum state represented by a vector in a two-dimensional Hilbert space. Quantum gates, which are the building blocks of quantum computers, are represented by unitary operators acting on these Hilbert spaces. The phenomenon of quantum entanglement, which plays a crucial role in quantum computation and quantum cryptography, is a direct consequence of the superposition principle, which is a fundamental aspect of von Neumann's formulation of quantum mechanics. Furthermore, von Neumann's work on operator algebras has had a significant impact on the development of quantum field theory and string theory. These theories describe the fundamental constituents of matter and the forces that govern their interactions. Operator algebras provide a powerful mathematical framework for studying these theories, particularly in situations where the usual methods of quantum mechanics are inadequate. In conclusion, John von Neumann's Mathematical Foundations of Quantum Mechanics represents a landmark achievement in the history of physics and mathematics. It provided a rigorous and comprehensive mathematical framework for quantum mechanics, which helped to solidify its status as a legitimate scientific theory. While certain aspects of von Neumann's work, such as his treatment of measurement and his theorem on hidden variable theories, have been subject to criticism, his contributions to the mathematical formalism of quantum mechanics are undeniable. His work has had a profound and lasting influence on the development of quantum mechanics and related fields, and it continues to inspire researchers today. The book serves as a testament to the power of mathematical rigor in elucidating the mysteries of the quantum world, a world whose inherent strangeness requires the firmest of logical footing. Von Neumann provided that footing, ensuring that quantum mechanics, however counterintuitive, stood upon a foundation as solid as any in mathematics.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.